we're going to get started now. So first off, hello, everybody. Thank you for coming to the tutorial today. I'm Eric, and I'm going to be teaching the tutorial on behalf of my co-instructor, Hugo. Hugo is right now based in Sydney, Australia. So Abigail, you're based in Newcastle, Australia. You probably know the pain. It's like pretty late right there, right now. Hugo's a little tired. I'm the backup person for the tutorial. The material he and I have created, mostly Hugo for this half of the tutorial. It's all about how do we do Bayesian statistical inference through simulation, all right? And how do we use simulation to help us understand our data and our models? So, we also have people from Hawaii where it's 4 a.m. right now. I totally understand the pain. Yes, I've been up that early before too. Okay, so before we go on, a few logistical matters. For those of you who were in the setup room before and you have a binder session up and running, the first thing I want you to remember is that every 10 minutes you should execute something inside a Jupyter notebook. All right. And the reason that we want to do that is because Binder has this timeout, right? It's a 10-minute timeout. And in that 10-minute timeout, you want, the reason it exists is because it's free compute resources, free being someone else paid. All right. Someone else paid. And so in order to conserve resources, there's this timeout that exists such that after about 10 minutes, I think it's 10 minutes or 15 minutes, whichever, one of the two, your binder session will be killed, right? And there's a reason for that, it's to save costs. So if you want to make sure you don't lose progress and don't lose work, make sure you run something every 10 minutes, and I'm going to do my best as well, not to blabber on for more than 7 minutes at a time. Okay. So, I'll do my best. Whoa, hold on. It appears that like we have issues with audio. All right. So first off, maybe we should like actually solve some of the more fundamental problems. I've got my mic set at a particular value. Can you all hear me? Can you hear me? All right. I'm just going to talk a little bit. All right, cool. Audio sounds great. This is good. All right. So for those of you who are experiencing audio issues, make sure you turn up the audio to max, put on headphones. That can help as well. One thing about online tutorials is that there's usually a round trip 5 to 10 second delay between when I ask for a response and when I get back a response. All right. So we're going to have to get used to that pacing. All right. And just want to make sure that is set there. The other thing is every time I do a screen share, like for example, now, you may see that the video quality might not look good. And this is a consequence of using an online platform. So one of the ways around this is I will use verbal cues to point you to where I am inside the notebook. And if you can't follow along, make sure you ping inside the chat so that you can get the attention of myself and Paul. All right. If I don't move around like this, usually then over a few seconds, the notebook quality will come back. Will come back. All right. And I'm already pretty zoomed in on my notebooks. If I go in anymore, it might help, but then I'd also sacrifice a little bit in terms of what I can display. All right. So I'll do my best over here on my side. Okay, so because this is a tutorial on statistics, we're gonna start off with a little bit about probability, because it's extremely fundamental. You need to be able to understand what probability is and how we use probability distributions in modeling situations. So the way that we're going to approach this tutorial is we're going to have, yes, I'm sorry, I should have put in a second reminder. If you go to the tutorial repository, which lives up here, and you go to the SciPy 2020 notebooks/SciPy 2020 subdirectory, you'll notice that there are 4 notebooks in which you are going to, which are going to be the focal point of today's instruction. There are really 2 of them, 2 pairs. One is the first notebook on what is probability, and 2, the notebook on parameter estimation. And there are instructor and student versions. The instructor version exists because that's where we created the material. And then the student version is where we deleted code so that you can actually get some practice by coding stuff up. Now, if you're ever feeling lost, you should not feel ashamed, because that feeling lost is a completely normal part of the learning process. What you can do is you can open up the instructor notebook and take a peek at the answers if you're genuinely feeling lost. Also, because I will be using the instructor versions of the notebooks, I will have the answers flashed up on the screen as well. And I'm going to be putting side by side the student and the instructor versions of the notebooks, all right? Just so that it makes it a little easier to follow along. And that gives me a way of, that will give me a way of identifying where the exercises are, okay? But that said, the answers will be up here, so you can take a look at those as well, okay? All right, so I'm gonna just get oriented a little bit. So first off, we're gonna kick off with a little bit of a discussion. What is probability? And what I'd like you to do is to type your answer inside Crowdcast. All right, so go ahead, take a stab at that question. What is probability, right? And what do you understand to be probability at this point in time? Measure of certainty about beliefs, the science of chance, the likelihoods of events, all very good answers. Yes, I agree. Likelihood of something happening, etc. Yeah, absolutely. So I'm seeing a lot of terms: likelihood, certainty, uncertainty. I'm going to take a stab at something over here. So this is a little bit of a departure from what we have in the notebooks. Moment. Okay, so let's see. We have quantification of expectation, activity over time, likelihood of something, possible set of outcomes, etc. These are all really good answers. The one that most of us probably were exposed to in our undergrad days was this idea of, if we have an event happening over and over repeatably in a static fashion, for example, the long run frequency of observing a value is the definition of probability, right? That is like our classical statistical training. And that actually is where the term frequentist shows up. Then there's also this idea of the belief of an assignment, a numerical assignment of belief or credibility points or something like that to values that happen, right? So what I'm going to try to do here is I'm going to try to open up and share my iPad screen. And the reason I want to do that is I'm going to try drawing over here something that hopefully illustrates what my current understanding of probability looks like. So let me just see here. The camera we'll use is this guy. Let's just see here. Can you all see my screen? My iPad screen? You should be able to. And if I start writing here, hello world, can you all respond back inside the chat that you can see or cannot see? You can see. This is great. We're good. Awesome. Amazing. This is good. I love this way of teaching. Okay, so the way I see probability looks like this. You can imagine I've got a space of outcomes. And the total area assigned to each outcome over all outcomes is 1. So, and then if I have, say, for example, a coin flip, what I do is I divide the area into half, and I say half of the area belongs to heads, half of the area belongs to tails, and that's a model for coin flipping, right? And so there's the total space of outcomes is in the big box. Individual, what do we call those? These are the individual possible outcomes from events. These numbers over here, I should draw them in white. These numbers over here, they correspond to what we call the likelihood of observing. Sorry, no. It is the probability of observing the event, the outcome, sorry. So there's I just want to be like extremely specific here. Outcome, an individual outcome is one of the possible set of values. Probability is a measure of like the tendency of an outcome to show up. And the total space of outcomes must equal to 1, right? So the total allocation of tendencies, numerical tendencies of producing an outcome must equal to 1. And this is the way that I view probability right now. Now, there's a term that also showed up inside the chat, and that is the term that even I got confused with myself, and that is the relationship between likelihood and probability. We'll touch on that in a moment, but I want you to be extremely clear that probability, that is this term down here, refers to the tendency of a particular outcome to be generated from a given probability model, whereas likelihood refers to the function, the math function that we use to evaluate data against a particular probability model. Okay, so I'm gonna do a quick pulse check. How are we on these two ideas? Likelihood, probability, outcomes, all of these ideas. Can you paste it? Can you type inside the chat? If you're doing good, give me a thumbs up. if you've got a question, let's ask that in using the ask a question functionality in Crowdcast. Pulse is 65, doing it. Great. Okay. So for the benefit of those who are having a little bit of issue with this distinction between likelihood and probability, I'm going to try one more example. Okay. I'm going to try one more example. And this one hopefully will become illuminating. Let's say we got a Gaussian, okay? We got a Gaussian. The space of possible outcomes is in blue. So is this blue line. So I'm gonna color that blue. And this is the space of possible outcomes. Okay. So this is space of possible outcomes. It goes from negative infinity all the way to positive infinity, right? So this is a second example. The total area is the total area of a probability distribution must sum up to 1. So this whole area underneath here sums to 1. Okay. One thing that is extremely, extremely important in the distinction between probability and likelihood is if I instantiate, for example, a model in which my center is of the Gaussian is 3, and I say it's got width of 2, okay, then I can evaluate data that comes in against this probability model for that data. So for example, let's say I have a bunch of data points that show up out over here. These are all the X's in green, if you all can see that. What the math function that I use to evaluate these data points is the height of the Gaussian at those points. I'm not using, I'm using likelihood as a way of calculating the likelihood or the credibility of those points under a mu3 sigma square 2 Gaussian model. Okay, this is not the probability of the data. This is the likelihood of the data. We treat the curve, which is this guy over here, it's the likelihood function. If we go back to the coin flip example, if, for example, I have a biased coin flip that is at 0.7 and 0.3, and I get a whole bunch of heads, it is very likely that I got this data from this probability model of 0.7 heads, probability heads. And so it's very likely, and we use the probability distribution allocation of masses as the likelihood. So there's a function that allocates it this way, and the height gives me the likelihood. However, it's the area that gives me the probability. Okay, so the height is what we use to evaluate data against this particular probability model. So I'm actually going to write that out. The math function to evaluate data against model, and probability is the tendency to generate data, well, sorry, an outcome. That we observe. Okay, so that's my attempt at clarifying these two, the difference between these two concepts. Now, in many settings, I've seen the terms used extremely sloppily, and that contributes to a lot of confusion when we're talking about probability versus likelihood. So there's a reason, it's for this reason that I'm going to probably come back to this point over and over and over again. Do we still have problems with this or issues with this clarification? So please let me know inside the chat.
Hey, Eric,
yes.
One question from Matt. With probability, I remember confidence as a key term. Can you use confidence to describe likelihood?
The answer is, I think we're conflating things here, but that's completely normal at this point. So we're going to touch on what we mean by confidence at a later point in the tutorial. Okay, Matt? Cool. And in case Ahmed is asking, I'm just using QuickTime Play, by the way. There are tutorials on how to do that outside. Okay, so having done my attempt at explaining what probability is and how it relates to likelihood, to our data and the likes, we're now going to go to the notebooks, okay? So let's go inside the notebooks over here and start playing around with some Python code that will hopefully illuminate these ideas for us, okay? So one way that we're going to explore this is by actually simulating probabilities. I'm going to do something actually. I'm going to launch Binder on my laptop as well. I should have done this a little earlier, but I'm just going to do that right now. And I'm going to see if I can code along with y'all, okay? Hopefully it loads fast for me. So let me see here. I'm going to do this. I'm going to have Binder launch on the side so we can just continue on while it launches. All right, so first off, we're going to try an exercise where we simulate what probability is by using pure numpy. So I'm going to have you open up their notebooks. If you could go to your notebooks and take a look at this section over here, simulating probabilities, I'd like you to try filling in the code block over there. So this is an exercise that I'd like you to do. So what we're going to do is we're going to use numpy's random number generator to generate floats between 0 and 1 and generate samples, okay? We're going to generate samples over here. So give that a shot. Make sure you get something that looks like this. Then when you're done, ping back inside the chat with like a thumbs up.
Hey, Eric, another question from David. Would it be fair to describe probability as the integral of the likelihood function over the selected domain of outcomes?
David, you are absolutely right. Now, of course, I have intentionally avoided using integrals and the likes in this explanation, and that is because I'm not, I myself am struggle a little bit sometimes with integrals. I still prefer discrete sums over integrals, but yes, that's the idea. All right, so I've got a bunch of people looping back with thumbs up inside the chat. You should get something that looks like this over here. And what we're doing here is we're simulating users, basically. We're trying to simulate users coming to a website and just say half of them click through from that website, go to the next thing. All right, so now what we want to do is to, from this population of 1,000 people, sort of pick out the proportion of them that have clicked on that button. And the way to do this is to actually identify those that have a value of less than 0.5. So keep in mind, we're doing this like discrete allocation of credibility points, right, from the uniform 0-1 line. And that's exactly what we're doing over here. So I'd like you to go on to the next piece over here and fill in those code cells and loop back with your answer. What is your proportion of people who clicked, right? Some will have 0.498, 0.465, some will have 512. Great. Someone hit exactly half. That's really cool. All right. So you'll notice we're not getting the same answer as each other necessarily, okay? And let's see. The reason why, oh, sorry. So someone asked if I can show line 2. By the way, Scott, in case you're able to, in case you get stuck somewhere, you can always look at the instructor versions of the notebooks on your side as well. Okay, so this is one way of what we would call of writing what we would call a data generating process. What's the logic here? We have a stochastic or like a random-ish data generating procedure that starts with the 0-1 interval. Okay. And on this 0-1 interval, we draw random numbers that correspond, that are just, random. We draw random numbers inside that interval. And then we take a threshold piece and we say, let's allocate a bunch of credibility points to one group and a bunch of credibility points to the other group. And that's effectively what we've done over here. And the reason we don't get the same answer as one another is simply because we're doing sampling from a stochastic sort of process. All right. So what we're going to go up to next is we're going to take a look at this next question. Let's say all that we had was this data, and we want to figure out and estimate what the click-through rate would be, right? So I'd like you to give it some thought. You can talk with each other inside the Crowdcast chat. What would your estimate of your click-through rate be given the numbers that you drew from that probability, that you calculated, the proportion who clicked? And I'd also like you to think about the next question, which is, how confident would you be of your estimate? This goes to the question that was asked earlier about confidence, okay? Give it some thought, then put your answer inside the chat window. Okay, so we see a few people who are making a pretty reasonable claim that we've got a single estimate, which is actually just the fraction that we calculated straight up. Okay. Paul is saying confidence is low because we only have a single sample? And the answer is, I guess it depends on what we consider a sample, but yes, if this was treated as a single trial, we might be correct about that. Portion times the number of clicks you're measuring against would be an estimate of the click-through rate. Possibly, yes, that's right. Confidence on one sample is quite low. That's depending on the definition. Okay. So Vu has another classical statistics viewpoint, which is how many percentage of samples would have the estimate interval containing the true value. And that is how we were trained in undergraduate statistics. Most undergraduate statistics would have trained us that way, exactly. And so Luke actually ran 3 experiments. Yeah, that's right. So, and found there are 3 different numbers as a proportion of people who clicked. And so now Luke is also getting into some of the long run frequency pieces as well. We could then calculate a standard deviation, as Derek is mentioning inside the chat, and that could be a way of handling it. Though I have mentioned, I don't know if I've not mentioned this in the tutorial yet, but I have written it elsewhere, that I once saw a Bayesian, a probability estimate that was 0.8 as the mean with plus minus 0.3 standard deviation. And then I knew, well, that's impossible, right? Like, it's impossible to impose my Gaussian frequentist approximate way of thinking on this problem at that point, because you cannot have a probability value that is greater than 1. So the usual way of representing an interval that represents our confidence level of our estimate is kind of deficient if we don't deal with the correct set of probability distributions. Okay, so yeah, if you try 0.8 plus minus 0.3 for the standard deviation, you get something really bad. You get the upper bound is 1.1 for a probability value. That's completely wrong. Okay, for those of you who are a little bit more mathematically inclined, Mike Betancourt has a very elegant Intro to Probability Theory link that is very good reading. It is a little bit dense on the math. So one of the things that I've been trying to hash as part of my own learning journey and as well has been to make it to do an alternate introduction that is a little bit more programmer friendly. Now, and Python friendly, so to in particular. And the reason for wanting to go to target Python is because, of course, we know it's a great language that is a very productive one for us to operate in. So, you can do so much stuff with Python that I think it deserves an introduction of probability that is on the level at the same level as what Mike has written over here. Okay. So we got some questions coming in as well. Couldn't we just bootstrap? And yes, that is another way of estimating the confidence level. Now, I see Edward's going on the path of yo dog. I heard you like bootstrapped, so I bootstrap your bootstraps to get greater and greater confidence. I appreciate the humor there. Yes. Bootstrapping is possible. We'll get there. All right. Let me post a link to the link. Let me post the link here one more time. Okay, cool. And thank you, Stephen, as well for doing that. Okay. So we're going to do now a second simulation, which is the one down below, which is, again, trying to simulate what will happen when we have a biased coin flip, right? So if you could all go ahead and take a look at that next exercise down here. Again, I'm clearly showing the solution up here, but take your time When you're done, put a thumbs up back inside the chat, and then we'll continue on. Mm-hmm. Okay, so I see a bunch of people finishing up. So what we've done here is, again, taken the space of possibilities from, we've taken an area in the interval 0 to 1, right? So we've taken an area, defined an area 0 to 1, and then partitioned it up into two pieces. And then we allocated part of that, a bias, like we allocated 70% of that area to, we allocated 70% of that area to one outcome and then 30% to the other outcome. And that, therefore, gives us a biased coin flip. So now what I'm like to ask you all in the chat then is, what other phenomena have you encountered in your day-to-day that corresponds to the biased coin flip situation? Oh, I like Kent's one. Likelihood that I'm modeling the number, the probability that one is wrong when arguing with your spouse. Stephen has the which hand I use to open a door. Yep. Okay. Seeing. Probably Christina has this neat one. I won't roll low. Probability that I won't roll low when trying to hit something while playing D&D. Okay, yes. And then Catherine has the plugging in a USB flash drive the right way. That's right. Oladimeji has a probability of dying of COVID-19. And yes, that is actually a very pertinent one, pertinent and contemporary one. Exactly. It's important. And so we can talk about it in terms of given a person, is that person going to have a higher probability or lower probability of dying? And we know that the probability of dying from a COVID-19 infection depends on quite a lot of important factors. Yes, absolutely. Okay, cool. And Grace has another one, which is whether a person will or will not support a cause. And you can see that, yes, we can allocate to individuals having credibility points of whether they'll support, which is heads, or not support, which is tails. And Solomon will do the final one. This is my favorite as well. Football matches, real football, not the one that's, hand egg played in North America. Football matches, which is actually played with your feet. Which team will win, right? Liverpool versus Man United, I think, is the bigger rivalry nowadays, a historical rivalry, but Liverpool versus Man City has been pretty intense recently as well, with all the money that's going inside there. Okay, so great. So you can see that the biased coin flip, simple as it is actually a pretty good probability model and very, it's a very versatile probability model. You can use it in a wide variety of situations. And that's, and one way, of course, that we've chosen to simulate this is by taking that area between 0, 1, and then slicing it in two, and therefore giving us our two outcome situation on which we can allocate probability. Okay, cool. I see the football rivalries all showing up in the chat window now. Let's keep it civil, everybody. All right. So next, we're going to go on to the next piece, which is the Galapagos finch beaks. Okay. So previously we had been dealing with binary situations. And so what we're going to do now is we're going to go into a slightly more continuous situation. All right. So this is, we're going to use the same idea of proportions, right? But we're going to try this with real world data that is not necessarily from the 0, 1 interval. Okay. So I'd like you to execute the next few cells so that we can import a data set of finch beak measurements taken from the Galapagos Islands. All right. So we know that the Galapagos Islands, extremely famous in the world of biology. We've got measurement of finch beaks. We have their length as well as their depth, right? Pardon me, let me just get a sip of water here. And so we can ask a few questions of our data and use that to help us with understanding probability and all that good stuff. So if we can ask the question, for example, what proportion of birds have a beak length that's greater than 10? So if you run the cell down below, you should get an answer that looks something like 0.85, right? And this, by the way, is the proportion of birds that have a beak length that's greater than 10 that's inside our data. This is not the exact probability value of like that a bird drawn from the population of beak length 10. So in other words, we've got what we've got from our data is an estimator of something that is true and hidden to us in the background. Does that make sense to you all? Right? Yeah. So and that's why we come to the next section down below, which is we've got this proxy for probability. Now, before we go on, I just want to make sure everybody's following along up to code cell number 8 that I'm showing in my notebook. So can you all just give me a thumbs up if you're okay so far? Okay, so we got people doing okay. Thank you for the feedback. We'll move on then. Okay, so a proxy for probability is exactly what we have over here. So when we get data which are assumed to be generated from a data generating process, that are assumed to be generated from a data generating process, we can approximate estimate of certain proportions. Sorry, we can estimate a proxy for probability from the data by taking proportions. All right, and this is sort of how we would call it hacker statistics. Right. So if you've seen Jake Vanderplas's talk from, I think it was PyCon in 2015 or 2016. He's got this hacker stats talk, which I think is which for me was also very formative in my view and understanding of statistics. So I'd really encourage you to check it out. if you open up the link that's over here, it'll take you to his talk over there. All right. Okay. So, and if you run this cell down over here, then you'll get another view of like how to an alternate way, of calculating. So we're at 45 minutes, and most of the time the human mind has a 45-minute, like in education. When I was in grad school, I took this class. 45 minutes is the limit for most of us in terms of like our mental capacity for continuous talking and learning. So what I'm going to do is we're going to take a 5 to 10 minute break. I'm going to spend the first 5 minutes addressing questions thus far, and then we'll go on to the next 5 minutes being like a bio break. Okay, 10 minutes. 10 minutes. Hassan, thank you. So we'll do 5 minutes for questions, and I'll just be typing at the chat window, and then 5 minutes for bio break. We'll come back and regroup at 10:58.
Awesome. Eric, we have one question. Can you tell us about this finch beak? What is this?
Yeah. Okay. So Suvik's question on the finch beak. Let's see. Finches are birds that live in the Galapagos. They live all over the world, but in one place they live is the Galapagos Islands, and they've been used as a model of evolution, as in evidence of that evolutionary processes do happen. So beaks you can measure, and they're evidence of adaptation, to the environment. Okay, so that's what this is about. So hopefully that answers the question. Okay, and Vias is, can we get people to post questions and ask a question rather than chat? And I think I'll do that. Okay, cool, great. And then there were questions of likelihood versus probability. And I think Charles has the way of understanding it pretty much nailed down. We use likelihood to evaluate our estimates. So I think the best way to do it is we've got data and we've got a probability model. We use the likelihood function to evaluate data against a model, and we use a probability mass or probability density function to generate data with certain propensities or certain tendencies. All right. And in most cases, they're actually the exact same math function. All right. So as someone pointed out earlier, if you have a discrete probability distribution, the binomial distribution, for example, with a 1 and a 0 and 0.7 for 1, 0.3 for 0, you would actually use the same probability mass function. You use those exact numbers to generate data with a bias towards heads. But at the same time, you also use those same values for evaluating data against the probability model. Okay, so hopefully that clarifies the difference between likelihood and probability. So probability is the tendency to generate outcomes assigned over all possible outcomes, and likelihood is the math function used to evaluate data against that were assumed to be generated from a particular probability model. It seems to me this is worth something that I've been working on in a branch of the repository. So stay tuned for a longer write-up. All right. So on that piece. And then Stephen has a question. We're talking about probability mostly as a continuous value, but in the case of finches, it's discrete. There's an integer number of finches in the real world. Does this cause any theoretical problems? I think when we hit large numbers, we'll be okay. And I'm intentionally leaking the term large numbers over there. So hopefully that, so in the regime of large numbers, that's usually fine. In a smaller regime, we might choose different modeling approaches. That said, the fact that there are an integer number of finches is sort of like, how do I put it? When we draw numbers from a continuous probability distribution, we're still drawing integer numbers of data points, right? So we're drawing small samples, large samples, etc. The values that we draw, though, are continuous, right? So finch peak lengths, we can model them. It's a modeling choice that we draw them from a continuous distribution. Okay. So Stephen, I hope that answered your question. Theodore has the question. So beak length is a proportion, not a probability, while the first two calculations were the probability that someone clicks on or not the site, the second being the biased one. If that is true, how are those measurements different? I mean, why isn't the first two ones also proportions? Well, the first two ones, what we did was we actually simulated data. Well, yes, actually, you know what? You're right. They are both proportions. And we're using proportions as a proxy for probability over here. In an alternate introduction, we would actually do away with, so there are multiple ways, as I've like explored the space of how do we teach Bayesian stats, there are actually multiple ways of introducing the topic. Hugo's got one with his notebooks. And it uses empirical data generation, simulating data, empirical data, and then calculating proportions as a way of illustrating what probability is. And the whole process that process is what we've used in the notebooks. If I were to do it a different way, we might choose to use a slightly more abstract, but maybe a little bit more generalizable way of approaching this, which is to say, well, it's a stochastic process. It's a stochastic process. Let's explicitly slap on a probability model and debate whether the probability model makes sense or not. And we'll use like SciPy stats distributions, probability distributions. So there's multiple ways. This comes from, I think, the way that we've chosen to teach it for this particular instance of the tutorial. We're using data which are either simulated to look like the real thing, data which are simulated to look like the real thing, or real data, and use that as a proxy for illustrating what probability is. So Theodore, I hope that answered your question. If it didn't, feel free to loop back. Okay, I'm going to take my much needed bio break now. So I'll see you all in like 2 or 3 minutes. Okay. Chris, thank you very much. I realize I set my microphone volume, input volume, to an extremely high sensitive one. So I'll be sure to keep that in mind. Thank you. Okay, so Oladimeji has a question. How does numpy.random choice work? Does it take the elements of lengths and randomly expand these exact elements in the size and samples, or does it use the stats of lengths to build a model and then sample data points from that model? For that, I don't have it on the top of my head right now. I have to check the docs. to see how it works underneath the hood. That said, random.choice is we pick an element from the entire array. We pick an element from the entire array, and let's see here so we pick n samples from the array of lengths, and if we say replace equals true, as others were pointing out, it allows us to sample with replacement. Okay. Thank you, Roy and Josh. Yeah, I think I misunderstood the question that was posted, and thanks Ola for posting that. And Kelvin is correct. You can provide a probability, I think, if so you can provide the propensity for each element to be chosen. Okay, Ahmed was saying the first coin example is confusing for me in the sense that the distribution was uniform in both the U.7 and U.5 cases. Yes, I think I can understand and empathize with where you're coming from with that. The uniform distribution is what we're doing there is we're defining space of we're defining an area. All right, we're defining an area over there. And then we're splitting the area into two. And then with the finch beaks, what we're doing is we're taking the sample of area, we're taking the sample of values, which gives us a proxy for the area, and then splitting that into two. All right, so it's sort of, there is that dichotomy in that, yes, where one uses the 0-1 interval and splits it into two. The other uses data and splits it into two, but really they're connected that way. So I'm going to take that point, Ahmed, into consideration as we do a update of the material. Okay. Okay, so we're at 11:03. I think we should continue going down. So as we go down, we're going to try another way to simulate coin flips, and this one is something that many of you probably have encountered before, which is the binomial distribution. Okay, so we're going to use the binomial distribution to help us tell a story of and express the data generating story. Okay, so what is this binomial distribution? It's got two parameters, n and p, and it describes the number of heads that we see flipping a coin n times when the probability of heads is equal to some value p. And it's a data generating story. The deep learning world is all about generative models at this point. And probability distributions, simple probability distributions like the Gaussian and the Bernoulli are data generating models in their own right as well, because you can run a data generating model infinitely, right? And you keep generating data from it. Okay, so Hugo's point on this paragraph here, I think, tells it pretty concisely, right? It tells a pretty general story. There's two outcomes. One outcome occurs with probability p. The other is 1 minus p. If you run this outcome n times, right, then you'll end up with the same. You'll end up with data generated from this binomial stochastic process, and that's this point down over there. Okay. So we can run an experiment with, or we can run a simulation. Let's call this what it is. It's a simulation of what kind of data we're going to generate when we do one run of a bias coin flipped 10 times. So I'd like you to try out this, run the cell down here. Okay. And then once we're done with that, I'd like you to go to the next exercise as well, and then plot the histogram of what you see over down there. All right. So if you could go ahead and take a look at that, and then paste back here in the chat window when you're done. Okay, so Edward is asking, what is the seed? The answer runs a little deep, but it's essentially there for reproducibility purposes. Okay, it has to do with how random numbers are generated. On a computer, you actually don't generate you actually don't generate genuinely random numbers. You generate pseudo-random, PRNG, pseudo-random numbers, right? So that's something for you to take a look at downstream later, but that's just know that this is for reproducibility purposes. Okay, so put a thumbs up when you're done with and you've obtained this histogram over here. Okay, I see the thumbs up coming. Thank you. This is great. Cool. So what you see over here is effectively what we would call the probability mass function, right? It's the PMF of the binomial distribution. And in particular, it is one instance or one configuration of the binomial distribution. So this is not every single binomial distribution looks exactly like this one. The binomial distribution for n is equal to 10, p is equal to 3 will look approximately like what we have over here. And I say approximately in particular because we've simulated the binomial distribution. We're not actually plotting the exact PMF, but it'll look something that looks like this guy over here, okay? If I had n is equal to 11, that's a completely different binomial distribution. And then if you have p is equal to 0.44, that is a completely different distribution yet again, okay? All right, so hopefully that is clear to y'all, all right? So that's what you're seeing over here effectively is the probability, an approximation of the probability mass function. All right, so now if we go on to what's down over here, the hands-on below, like you attempt this next set of exercises too. And then when you're done with that, we can loop back here. And so Ahmed, yes, it is possible to draw the exact PMF. And in a rewrite of the tutorial, so once again, stay tuned for the updates on the repository. On a rewrite of the tutorial, we'll actually be emphasizing the fact that you can calculate and draw the PMF exactly. So when you're done, loop back inside the chat and put a thumbs up down below.
Hey, Eric, a question is asking, why does the distribution look normal?
Yes, so Jishan has the question, why does it look normal? And there's a reason for this. It's so some people have made that observation, and what's been noticed is if you have a high enough n and a reasonable p that is like close to, not at the extremes, you get an approximately normal looking probability distribution, but you have to be extremely clear with yourself. It is an approximately normal. It is not exactly normal. All right. So Jishan, I hope that answered your question for you. Okay, we're going to wait for a few more thumbs up. Oh, okay, wow. That's actually new. So Crowdcast blocks using the same message more than once in a while. All right, I actually didn't know that. So cool. We'll chime in somehow with something saying that you're done or you're good to move on. Okie dokes. Thank you all. Thumb 1 and thumb 2. Right thumb, left thumb. That's all good. Thank you very much. Cool. So now if we were to give you this histogram over here, you'd look at that and you'd see, well, okay, I've got my, on the x-axis, I have the space of possible outcomes. I like that. Crowdcast should sample thumbs up and thumbs down, then calculate probability. Cool. So whenever you plot a histogram or you plot the PMF, visually, you keep in mind, you're plotting the range of possible outcomes on the x-axis and their probability, or the height corresponds to the likelihoods. I'm just going to put it that way. The likelihood on the y-axis, okay? And that gives us the probability mass function in a discrete case versus a probability density function in the continuous case. Okay, so now one thing that's, I think of, we're going to talk about a pretty pragmatic thing before we go on to talking about probability distributions and their generative stories, like what stories they are describing. And this pragmatic thing is calculating, or visually inspecting and checking, the probability of seeing a particular range of values. So if you look at this histogram over here, it's kind of hard to say what the probability is of seeing 4 or more heads, or say 8 or fewer heads, etc., out of 10 coin flips. Okay. So that's why we have this thing called the empirical cumulative distribution function, right? And we can plot the empirical cumulative distribution. And it offers a bunch of advantages over using a histogram. So let's take a look at what the ECDF is all about, right? So this ECDF can be defined using a function that looks something like this guy over here. So if you scroll down in your notebooks, in the student notebooks, you'll see that we have that. Sorry, let me just come back to where I am in the student notebooks. So in the student notebooks, you'll notice this function exists over there. You don't have to write it. So what we're going to do is we're going to have you plot the ECDF for this particular data set that we generated above. All right. So go ahead and fill out that cell. And then I'd like you to try to answer the question one more time, which is, what is the probability of obtaining 4 or more heads based on the ECDF? We'll do this before I go into explaining exactly what the ECDF is. So if you could, once you get to this point, loop back in the chat with your answer approximately. What's the probability of obtaining 4 or greater heads? Yes, I see the answers coming in. It's all looking very good. Approximately 0.8. Yep, that's right. And can I just quickly check? How many of you think you would have been able to get that answer from the histogram? If you think you could, put yes. If you think you couldn't, or you would have difficulty, put no. I like Michael's answer. Eventually you probably could get to a reasonable guess, but not as easily as with the ECDF. So let me explain to you what the ECDF is, okay? So the ECDF, this is also for Paul B's benefit. What we're doing here is we're visualizing the distribution of our data using using the ECDF instead of the histogram, okay? And what the ECDF tells us is the cumulative fraction of data points that have on the y-axis. The ECDF tells us the cumulative fraction of data points that have a particular value or less, okay? So in this particular case, the value 3, 20% of these values have the value 3 or less. About 40% of values have the value 4 or less in the data that we have. About 65-ish percentage of values of data points have the value 5 or less. That's what the ECDF is visually showing to us. So if you think about it, the ECDF actually makes easy visual inferences on our data. So for example, what is the median? Well, the median value is defined as as the value for which that 50% of values have that value or less, okay? So we go to find the median, we draw a horizontal line from 0.5 on the y-axis to where it hits the data and then drop a value down. And then we see that the median is equal to 5. I can ask for what the 80th percentile value is. And the 80th, pardon me, the 80th percentile value is this guy over here. So we draw a line from here to the data and we drop a value down and we see the 80th percentile value is 6. And then the 20th percentile is over here. So to find out the probability of observing 4 or more, you actually take the value 4, see where you hit the first value over here. You get to about somewhere on the y-axis, and then you calculate, because we want or more, and because the values are ordered on the x-axis, we actually go take the total height represented by all of the values that are 4 or greater. Okay? Cool. So do we have any questions about that? So why are there overlaps? And that's what we're doing here is we're actually plotting every single data point. Okay. So the way to think about this is not actually vertical bars. This is individual scatter plot points. And I want to very quickly address why we call this the empirical rather than just the CDF. It is empirical if we generate it, if we plot the CDF of our data. It is non-empirical, for lack of a better word. It is true CDF if it was generated, exactly, Stephen, thank you, generated from theory, not by simulation, not by our data. Hopefully that makes sense to those who asked it. Ahmed, I hope that makes sense to you. And then the next question on this one, do I see ECDFs as a replacement for histograms or as a supplement? And here's where the practical application of ECDFs comes into play. Most people grew up on histograms. So for communicating distributions, histograms are actually the thing that most people will get tuned into first. However, they'll also make a ton of mistakes with interpretation on a histogram. So that's why I think it's always great to show the histogram and then show the ECDF show the histogram of the data and then show the ECDF later as well. I've argued in a blog post that it's actually much easier to lie with a histogram than with an ECDF. And for that reason, I try to train my colleagues to use ECDFs as opposed to histograms, but it does take a little bit of education. So hopefully, Michael, that answers your question as well. Okay? Okay, so Esteban had that question. Can you comment on vertical line versus having a point plot? I think James's response earlier up above, where he shows what X and Y are, should give you the best explanation of what's happening inside here. We're plotting individual data points that are from our X data point, from our X vector. Okay, Xavier, I'll get to your question in a bit. So that's why, and because it's the cumulative number of points, if you go up over here, this is a sequential ordering of all of the values, all of the data points that have the value 4. So you'll notice approximately 22% of values have the value 4. And so if you go down, if you rank order all of your data, it's sort of like, let me just stack up all of the values as I go along until I move on to the next one. I hope that sort of illustrates I hope that illustrates it clearly enough for you, Esteban. And for those of you who are asking for examples of how you can lie with histograms, Paul, thank you. You put up like a blog post that I wrote in 2018 on this exact matter. So thanks a lot. Okay. Cool. So now that we're done with ECDFs and this very little practical matter of, so let's see. Now that we've got now that we're done with the ECDFs and this practical matter of like how to visualize your data and its distribution, we're going to walk through a few examples of other probability distributions and they're generating data generating stories. Okay. So we're going to go down to this next section over here. There is a Caltech instructor, Justin Boyce, who has been extremely wonderful person for me and Hugo in our discussions about and learning journey about probability distributions. He actually has this extremely great resource. That tells us about the data generating stories of a large variety of probability distributions. I'm going to see if I can find the link over here. Just give me one moment. Justin Boyce, probability distribution stories. I'm going to paste that link inside over here for everybody's benefit. For those of you who are fans of bokeh and interactive plotting, he's got the whole things over here, the whole swath of stuff over here. Let me just see here. So he's got bang, bang, bang over here. For example, the Bernoulli distribution that we had just explored and played around with. He gives us what the story is and an example of it, what the parameters are, and how we can use them in different statistical modeling languages. Okay? Cool. So that's a great resource. And in fact, this section on probability distributions and their stories is highly inspired by that resource over there. Okay. So, yes, Ahmed, that's sort of the resource that we all need when we're dealing with probability distributions and writing statistical models. All right. So let's go on and look at Poisson processes and the Poisson distribution. Okay. So Poisson processes are processes that give us count data, discrete count data, and they tell us about the number of things that happen over a certain, they give us a rate of things that are happening in a single unit of time, right? So one example is the number of births, natural births given in a hospital, or the number of, the one that I learned when I was in grad school is the number of car crashes at Brigham Circle near Harvard Medical School. I did a stats course at the School of Public Health. So this instructor used that example. So Poisson process, the Poisson distribution, can be used to model the counts of certain events happening on a per unit time basis. All right. So we're going to look at this down over here. If you could do this little exercise over here and take a look at what it looks like. Try to generate a plot down below. Then we'll go and launch into a little bit of discussion. Okay, so when you're done, put a thumbs up or some kind of chime in on the chat. Cool, thank you all. See Maggie and Theodore's done, Ivan's done, thank you. All right, the thumbs ups, the sunglasses, they're all coming in. That's amazing. I see everybody's getting creative with the emojis. This is great. So, question. This question that is down below there is, does this histogram look like something you've seen before? Actually, I think if you think a bit about it, it looks quite a lot like the binomial distribution, except when it's done in the limit of, low probability of successes, large number of trials, i.e. rare events. And if you think about what's happening, here's what's happening with the Poisson distribution. It's almost as if per time step, you have a per infinitesimally small time step, you have a very small probability of distribution, probability of heads happening. Then as you add up the these really small time slices, you end up with this data generating process, which is like every so often I have a low probability of generating an event, so that when I sum it up over a larger slice of time, I get X number of events on average. Okay. So that is, that's what's happening with the Poisson distribution. And in fact, I remember using this to discovering this for myself when I was just playing around with it, and then playing around with the Poisson and the binomials. And then I asked one of the professors on my thesis committee, like, what is this? And then he explained it exactly as the way that I'm trying to share this with you. The Poisson distribution is effectively the limit of large N, low probability, repeated over and over and over on a larger time scale, right? So you can actually simulate a Poisson distribution using a binomial distribution. It's like kind of mind-blowing when you think about that. So some questions that are showing up, is the appearance of the histogram strongly tied to the bin size? And the answer is yes, which is why it's so easy to lie with a histogram. You can actually hide outliers, as an example, by using the right bin width. Okay, so yeah, that's just something to keep in mind. So let's try the exercise below, which is plotting the ECDF of Poisson distributed data. And then we'll go on to the next exercise below right after that, which is field goal attempts per game. Okay, so go ahead and attempt those two exercises, right? And you should bring yourself down to this point over here. And for the benefit of everybody, I'll just type out over here. Let's do exercise on Poissons. You should see what is on my screen. And then loop back with a fish or wine glass or whatever you want, emoji you want. Apologies, I had to do my own bio break as well. So yes, I see a lot of people. I see the fun emojis coming up. Awesome, y'all. Really good. So what you can see, what we've done over here with this code block is we've actually simulated Poisson draws. Okay, and we've plotted out the ECDF of our Poisson draws, and we've done a little bit of uncertainty calculation as well while we're at it. Okay. And so this gives us, what we've done here is we've actually compared the uncertainty, we've compared the ECDF with its associated simulated uncertainty against the field goal attempts by LeBron James. And this, just so you know, comparing ECDFs is a great way to check to see whether your data may have come or may be possibly drawn from a particular probability distribution. However, if you look at Alan Downey's blog post, which Paul posted, I think, earlier on in the chat window, you'll notice that he makes the claim that you can never be 100% sure that your data were drawn from a particular probability distribution. You can do statistical checks. You can use the statistical checks to inform your judgment call about the modeling exercise that you're trying to do, but you can never really be 100% sure. Okay? So I'm just gonna, because I see a bunch of people having video issues, I'm going to write down in the text chat window what I just wrote there, what I just said. Checked our data against the ECDF. And found that they matched. And yes, Ahmed has the exact point I'm trying to make. You can know that it is quite likely, in fact, even most likely drawn from a Poisson distribution. Data are drawn from both Poisson or Binomial or something else. You can know that it's most likely drawn. You can never be 100% sure, but on the basis of your modeling exercise, you can then make a judgment call. And Charles also makes a very valid point. Yes, there is no evidence that the data do not follow the model. Exactly. Okay, cool. So that's the Poisson distribution. Just wanted to introduce the data generating story for you, which was number of discrete events that are happening over a unit amount of time. Okay. Could we replace the Poisson? Theodore has a question. Could we replace the Poisson with another to verify that the data are definitely not drawn from a model? Well, what you can do is you can make the qualitative claim that it's kind of not, like if you plot the ECDF of the binomial, you actually might get something. Nah, binomial is a bad one. You try another one. You could try the negative binomial distribution. And if you try the, sorry, a little thirsty. You can try another discrete probability distribution and try to see whether the ECDFs are close or not. And Lou's question is quite valid. Is there, because I think it relates to the broader point of like what quantitative ways can we use to compare, right? What quantitative ways? There are a few. I've used a few in my work, all depending on who I'm talking with and what the problem is. The first way that I've tried has been to use just to calculate the likelihood of the data under different probability models. So for example, if you changed the mean of the Poisson, then, okay, well, it'll look different. If you did what Theodore did, which is to completely change the family of the distribution, that would also be another way. And you can actually evaluate the likelihood of your data under a different set of probability models. We didn't do that over here right now. We're just using a visual check, but that's the other way. You can calculate the likelihood. Also, another way that you can do this is you can generate samples from an assumed distribution and then compare the Earth movers distance between the two of them. In SciPy, SciPy Stats has this. SciPy Stats, Wasserstein distance. SciPy Stats library has a Wasserstein distance, which computes the distance between two distributions. That's another way of doing. So that's another quantitative way that can be used. All right. So let's see. I have a choice to make. I think I'm going to, Jishan, I'm going to leave your question to the end because the binomial and negative, actually no. What I'm going to do is I'm going to point you to Justin Boyce's probability distribution stories, because that's the place where I think the negative binomial distribution story is described. And if you read that, that will compare, you can compare the two stories, okay? Atharva asks, can we use KL divergence? That's another good metric to use as well. I think the metric that you use depends on the problem as well, all right? So just keep that in mind. And then the final one from Gary before we move on, are all distributions known? Kind of a philosophical question, right? Can we know everything there is to know about the universe? I think there are enough probability distributions for practical use that are pretty, like there's a catalog of probability distributions that are well described that can be used for a wide variety of modeling scenarios. So for example, at work recently, I had to deal with probability distributions over the angular space. All right. So there's another one. So there's a probability distribution that describes rotational probability or likelihoods assigned over the minus pi to pi interval. All right. Okay. And Ahmed has another one, which is, would I be able to say that Wasserstein distance be more accurate than graphical visual evaluation? Paul has answered it. Thank you, Paul. So Wasserstein gives you a single number, but doesn't tell you about qualitative differences. All right, so let's move on to the exponential distribution. The exponential distribution gives us another story, and it's one of the family of continuous distributions. This one relates to the waiting time between Poisson process events. Okay, does that make sense? All right, so let's see. The number of buses that arrive per hour are Poisson distributed. So in this example here, in Poissonville, if we're modeling bus arrivals at a bus stop, the number of buses that arrive per hour Poisson distributed. However, the waiting time between bus arrivals are exponentially distributed. Okay. So I'm going to do this with, I'm going to attempt the next exercise below. So loop back with emojis, flood the chat with emojis whenever you're done. And by the way, I think we did have this piece inside. There's a comment above in the chat asking us to move the questions into the Q&A box as opposed to putting them in the chat, because I think we're now coming to the point where we realize, yeah, we need the chat to be able to pace the tutorial. And if we flood the chat with emojis, it's going to be hard to catch up on the questions. So let's do that. Let's do questions inside the Q&A box, and we can do additional comments and emoji flooding in the chat window. Okay, so you could finish off the section, the exercise that has to do with nuclear power accidents, and make sure you hit this piece over here. All right. So Atharva's question, is there a general way we represent all known distribution? I know distribution or a specific version of a more general distribution. Well, there is this graph that I remembered. What do we call it? There we go. John Cook's website. Ah, there we go. I remember this one. Okay, so while everybody is doing the exercise, I'm going to address one other question, which was a really great one inside the Q&A one. Is there a way to know if distributions are a more specific version of a more general distribution? Yes, these distributions have been defined and derived by mathematically oriented statisticians over history. I pasted inside the chat Q&A as a comment a link to John Cook's website, which is this one, that gives you this diagram of the relationship between probability distributions. And in there, there's a link. Sorry. And in there, there's a link to a much more comprehensive chart, which looks something like this. And this is just an amazing resource. So one example I know of is like the uniform distribution is a specific case of the beta distribution with certain parameters inside there. And the normal distribution is actually a specific case of the student's t distribution, so the student's t distribution is actually the general case, and so is the Cauchy distribution. The Cauchy distribution is a special case of the student t distribution. Okay, so that's hopefully the chart. Paul has put the links up in the chat, so go take a look at them, archive them for your reference. So you should see. Once again, we plot the ECDF of, so back to the exercise, sorry. Once again, you see that the ECDF of of an assumed exponential distribution looks something like this, and that the time between nuclear accidents appears also to be distributed by exponentials, all right? Exponential distributions. And I like Paul's comment that, yeah, make this into a tattoo. It's totally, that would be a painful one to write, I imagine. Plus, I'm not sure I want a tattoo when I want to be able to go inside an MRI machine, just in case something happens, right? Okay, so next one, the normal distribution. Okay, so we're going to do one final exercise before we take a break on the normal distribution. So, this is the bell curve. Actually, you know what? I'm going to simply describe what the normal distribution story is. It's probably faster this way. So the Gaussian appears of any quantity to describe any quantity that emerges as the sum of a large number of subprocesses, and they tend to be normally distributed, as long as none of the subprocesses are broadly distributed, like they don't have a wide distribution. Okay, so here we have the speed of light measurements, and lots of people have made measurements of the speed of light, and so we've got that guy over there. Looks Gaussian, and if you plot the CDF, it'll look like that. Okay. We're going to stop here once again for a bio break. All right. And what I'm going to have you all do is, again, post questions for the first 5 minutes. And then the next 5 minutes, I'm going to do a bio break myself. We'll come back at about 12:01 or in 10 minutes from now. All right. Okay, so first question by Ahmed is, what do we mean by none of the subprocesses are very broadly distributed? So let's see. If you think about the data generating process, like we want to estimate the speed of light, the way that we generate measurements for the speed of light, they all tend to converge on a pretty tight bound or a tight region, of continuous number space. So it's sort of like, generally speaking, we don't expect the number to be wildly out of like a whole order of magnitude off, for example, or, half the variance. Whole order magnitude or half the scale off. All right. Hopefully that answered your question. I think another way to think about it is like every measurement that you have has like a reasonable bound on the highest, region of density, for example. So, the measurement of light is like 3 times 10 to the 8. Thank you, Paul. You're giving me the right words. Your data tails fall exponentially. Yeah, that's it. That's it. Thank you. I think that's the best way to approach it. I'm really sorry. I'm starting to get a dry throat right now. So I'm going to go grab some water real quick. Okay. Okay. I'm back. All right. So what's some questions? Theodore's question is, what's the large number of subprocesses when measuring the speed of light? And Robert has the correct answer. Your measuring equipment are many different pieces, each not perfect, but they're all pretty close to one another. So thank you very much, Robert, for answering that question. Next one, Bipratip has the question, in the examples where we sampled from the data sets, is there an underlying assumption that the data gathering process, or I'm assuming you're meaning the data generating process, was unbiased? And the answer is, we're assuming that our data generating process was from a particular distribution, yes. And I think when you mean biased, you probably actually mean skewed, right? So that's something that we have to make an assumption of. So the act of making an assumption, you're absolutely correct. So hopefully that answers your question. And then Craig has the question, sorry, one moment. Let me just fuel up with some water. Craig has the question, why does the Poisson distribution not include a width? And how do we handle orders of magnitude in the mean? And I think Ming has the right answer over there. It's defined without a width parameter. So I think if you look in the SciPy stats library, as well as TensorFlow probability, there's a tendency to describe distributions either by their location or their location and scale. Location refers to the mean. This is, by the way, a pragmatic thing for you to keep in mind. Location refers to the mean. Scale refers to the width of the distribution. And the Poisson is defined by definition as only having the mean or the location. If you want a discrete distribution that has the ability to capture both the location as well as the width, then you probably want to move into what they call a negative binomial distribution, because that is an example of a distribution that gives you the ability to control the width or the scale of the distribution in addition to the central tendency or the location. All right. That said, we also have to be like a little cognizant of what the data generating process is. So I did, and the reason I want to mention this is because I'm actually thinking back to, I think this was 2018 SciPy, when I sat down with a fellow data scientist from, I think it was TripAdvisor, and we were just looking over some toy data that he had on hand. So it wasn't his real company data. And when I saw it, oh, it counts. It's got to be a Poisson distribution, right? So we like built a model that used Poisson distributions as our data generating process. And I was wrong. I was completely wrong. And he and I looked over it, and we actually did all of the checks that you saw thus far. We looked at the data generating process posterior, like we looked at the CDF of the data generating process and compared it against the data and was like, it's completely off. I have no idea why. And we didn't realize that, actually the Poisson is the wrong data generating model. It's like, we're not concerned about things per unit time. We're actually concerned about a process in which we say a number of things don't happen until they happen. And that's what the negative binomial distribution actually describes. So it was for me a lesson in like, okay, now we can't just look at what distribution is there. We can't just assume that our distribution would be the right one on the first pass. In fact, we've got to do all these checks to make sure. Okay, so hopefully that answered the question about like the Craig's question. And then DDOF, let me just see here. Denominator degrees of freedom. Binod, I'm not sure where that came from, but Charles has the right answer. So I'm going to skip addressing the question on video because I'm not right now unable to connect it to the notebook. And then Niels has the final one. At what point do we decide that a measurement is a physical constant, like the speed of light? That's a deep philosophical question as well. My viewpoint of the world has been we gain better and better estimates of the true value, but we're never like 100% sure. And I'm going to maybe reveal a little thing for what's going to show up later. So let me just see here. Let me just draw something really quickly. On my screen, when do we know that we're kind of sure? Now that we've talked about a little bit about the variance of a distribution or the width of a distribution, how do we know we're sure? How do we know we're unsure? How do we express quantitatively that we're sure? How do we express quantitatively that we're not sure? Imagine we got a Gaussian. The distribution in which we are sure looks something like this. And the distribution in which we are not sure, or we're not so sure, looks something like this. And the distribution that says, I really don't know. Sorry. Looks something like that. I hope that this gives you the qualitative way of understanding, like the qualitative way of understanding how we express certainty. Okay, how we express certainty in our using probability distributions. So we're really certain about something, we actually have a very small variance. And if we're really uncertain about something, we express it by saying, let's slap on a lot of variance in the distribution. So hopefully that makes sense to everybody. Yes, Simon is like, I really don't know, should be a flat uniform line. On the infinite space though, you actually get, what do you call the PM.flat, an improper distribution that goes from negative infinity to positive infinity with zero everywhere. It's an improper distribution because I think by definition you don't have any area underneath the hood, but it sort of is a practical way of expressing that. And then John is like, what if you don't know? If you don't know, then you run into Rumsfeld territory. And for the foreigners who might not understand the reference, that is a reference to some American Secretary of Defense, I think Donald Rumsfeld or something like that. Yes, where he said, there are things you know, the things you know, then there are things you don't know, and there are things you don't know. So, yeah. Oh, well. Okay. The next piece down below, after the nominal distribution, is all about joint and conditional probability. I would like to, let me just see here. Actually, before we go on, I need to check on the time just so that I'm mentally correct about, I have the right mental model. Emily, can you inform us what time we're supposed to end? Or Paul, if you do remember what time we're supposed to end? I'm sort of losing track of time myself now.
I think technically this goes until 1. We'll see how many people decide that they want lunch.
Okay, it's 1 p.m. Central, right?
Sorry, 1 p.m. Central, that's right.
Okay, that would make it 2 p.m. Central. So we're only midway through the tutorial. All right, so hopefully you're okay. Hopefully you all are okay so far. I haven't bored you out yet. So the next piece that is down here is on joint and conditional probability. We could go through it, but I think there are, the connection for us from joint and conditional probability to Bayesian statistical inference, I might have a bit of an easier time explaining it in drawings. Okay, so I'm going to use that. So while I do that, I'm going to have you all reminded that you should refresh or execute something in your notebooks on Binder if you're using Binder every so often, every 10 minutes or so. Okay, so when we talk about a coin flip, right? We get data that looks something like heads, tails, 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 heads, heads, etc. Our data are distributed / configured in a particular fashion. The thing that we observe, one realization, one instance of our data has this particular configuration in which the heads was the first, followed by 3 tails, followed by 2 heads, etc., etc., etc. We assume that it is generated from from a particular model. And say, for example, we generate these from a distribution we didn't cover, but looks extremely similar. No, I shouldn't introduce things. It's going to be called Binomial 1, P. Okay, so this is the generative model that gave us our data. So sorry, I'm going to move this down below. Oh gosh, that's bad. Let's try this again. Take this guy, shift it down. And so the binomial 1, P gives us our coin flip data. One possible configuration, sorry. One possible configuration. Okay, so what I'm going to ask you now is this next question. How many possible generative model configurations exist? So that's the first question. How many binomial 1p models exist? Okay. The next question I'm going to ask is, how many configurations of data exist? So I'd like you to reply back in the chat when you have an answer. This one does take a little bit of time to think about. And Ben is asking, is HT that the same as TH? And the answer is no. Christina has a question. It is not a stupid question at all. So please don't label your own question that way. What does the 1 refer to in the binomial 1p? It is 1 refers to the number of draws from the binomial. So it's actually n in the binomial distribution. Okay. Okay. I'm starting to see a number of responses over here. So this is really cool. People are saying there is an infinite number of models and a large number of data configurations, right? Yeah, that is correct. So in other words, you can think about it this way. Remember, when we go back to our notion of probability distributions above, probability distributions, we're concerned with spaces of possibilities, spaces of outcomes. If you think about the number of configurations that are possible for a binomial 1, p model, there's actually an infinite number of possible configurations. There's an infinite number of possible configurations of binomial distributions with n is equal to 1, but p is not precisely known. Similarly, for the coin flip, there's a large number of ways our data could have been configured. Okay, so there's a large number of ways that our data could have come to us. And so, once again, there's this space of possibilities. I think that sounds kind of familiar. There's a space of possibilities for our probability distributions, and there's a space of possibilities for our data. Okay, so what this means is when we model, when we say we're not precisely sure about the value of p, does that make sense to people? I want to pause for a moment and get a pulse check. This idea is actually extremely crucial, that the fact that there's an infinite number of possibilities for the data, for the generative model, and there's a large number of possibilities for the coin flips, and we're dealing with one of them. Can you think about it and write down in the chat whether you have a problem or not and what you think you might need a clarification on. Yes, so Steve's question, you mean we can't precisely estimate P based on the data? Yes, and I have an extremely precise definition for what precise means. Precise means I know exactly what the value of P is, and there's zero uncertainty around it. When I say we cannot precisely know it, what we're saying is it takes on some value with some probability distribution, but you won't really ever know exactly which value it is. This versus, so this is not precisely known. And for good measure, I'll just add a really not known. Versus precisely known. Okay. Theodore asks why a large number of configurations and not infinite. It's infinite if we assume we have infinite number of draws, but I guess I'm being a little bit sloppy. Thank you. If we have a finite number of draws and we have a finite number of possible outcomes, then we have a finite number but large number, right? So then Gary has this question, would you say that the delta as delta approaches zero makes P minus E really hard to estimate within that interval? I'm not 100% sure, Gary, what the question is, but let's take a clarification question in the Q&A, okay? And then inside the Q&A, Simon has the question, is it infinite because P is continuous? You hit the nail right on the head. That is absolutely it. Okay, so P is continuous, therefore there's an infinite number of possibilities because I can have P is equal to 0.5, I can be P is 0.51, I can be P is 0.511, P is 0.151111, and you get the drift, okay? And then another off-topic question that I'm seeing is, what drawing app is this? This is just the regular Apple Notes on the iPad. Then Benjamin's question is, what about the central limit if you make an infinite number of draws? Sorry, one moment. Let me get some water here. I think Paul has the response right there. Your sample distribution gets closer and closer to being normal shaped. And your estimate for P gets closer and closer and closer to looking like a delta function, which is exactly what I had drawn up there. Okay? Okay, so now we did talk a little bit about, okay, so this point on like how precisely do we know a parameter? It's visually looks like this, all right? The fact that we have spaces of models, models and spaces of data, that also very important. Now, when we talk about Bayesian statistical inference, we are imposing a joint model between sorry. This is a very hard thing to write because of the overloading of terminology. We're talking about the jointly distributed space of model and data configs. Okay. So far, so good. All right. Yeah, someone says, you click play, you get to see me drink over and over again. Yeah, that's seems to be the thing that happens. So I want to make this really clear. We make a modeling choice every time we say that we write a joint. Every time we say we think our data came from this particular distribution, we're making a modeling choice. We're choosing to jointly model the space of possibilities of our models as well as our data. Okay, the joint space. We're modeling it jointly. So, okay, Bharat had the question that yes. All right, Paul has taken that. Thank you very much, Paul. Okay, so when we talk about like a joint distribution, I think there's a visual way of understanding it, right? And the visual way of understanding this is by taking the classic bivariate Gaussian distribution. Okay. This is what we would call collectively the joint distribution between two Gaussians. There's an infinite range of space of possibilities, possible outcomes, and then there's a particular space, another space of outcomes on the y-axis. And here's where this notion of joint and conditional probability comes into play. When I say I model something as being joint, the visual image that should show up in your head is something that looks like this guy. Okay, that's what should show up in your head. However, when we talk about we're conditioning on a known value from one of the two variates or one of the two random variables, we're saying given a known value of one of the variates, what is the distribution of the other? Okay. So far, so good. So far, so good. So now here's where it gets really cool. If you understand what conditioning on looks like when it comes to doing, when it comes to like looking at the Gaussian, like the bivariate Gaussian case, by analogy, we make the case that we swap this out for our data, which is one configuration of data. And then we ask our parameter space. What does our parameter space look like on the abstractly condensed to one axis? What does our parameter space look like when we condition on the configuration of data that we have obtained? Okay, so do we have questions about this piece? I need to get a little bit of feedback here to know whether this makes sense to people or not. Okay, Catherine says you're gonna have to let that sink in for a little bit. I completely empathize. And there's a reason why it took me it took me about a year and a half of thinking, working on problems, rethinking, and more to really grok this. Okay. So I think you should definitely take the time and really think hard about this. The question that Ian has on over here is, what is the param on the y subbed in for the other distribution? In our particular case, it's the not precisely known parameter. So in our case over here, P is not precisely known. Therefore, in this particular example of inferring P from a joint model of binomial 1P as well as our data, I would sub in P over here. What does P look like? And then, of course, the space of possibilities is abstract, but still pertinent in that, like, it's the idea that there's a space of possibilities from 0 to 1, even though it's not exactly like the bivariate Gaussian, which is infinite space. Okay. And then now let's see. Kelvin has the question, can you explain the difference between conditioning and marginalizing? I'll give you the short answer. Marginalizing means sum up all possible values. It's like, what's in the margins? It's this. This is the marginal distribution. It's the distribution of one of them, ignoring the distribution of the others. Sort of like just summing over every other possible outcome. Okay. So Kelvin, I hope that answered your question. Next one. So when you have the case of known value of 1 as the variance, is that what you refer to as conditional probability? If not, if I'm not wrong. Suvik, it's actually, this is our data. We have one configuration of data. We know n is equal to 1 precisely because that's a modeling choice that we've made. But what we're really interested in is the value P. Which one? Which we don't precisely know. So we need to know. We're conditioning P on the data. Okay, so then let's see, let's move, oops, sorry, I moved that. And then Antonio had the question, so we are conditioning on one's variable outcomes and analyzing the other variables distribution as a parameter in the case of bivariate analysis. Antonio, if you struck out the last sentence, which is in the case of a bivariate analysis, you actually have the entire concept correct in abstract terms. I'm using a bivariate just so that we know we have a sort of a visual way of explaining what we're doing when we're doing Bayesian statistical inference. Okay. Theodore's question is, what does it mean conditioning on the data? It means we really want to, we've made, we made a modeling choice where we're going, we've observed one value or one configuration of the data, and we want to know what the distribution of our parameters look like having seen the values of the data that we've observed. So the analogy, I'm using this as an analogy. If in blue you have the bivariate Gaussian, and we say we're conditioning on one value of the vertical red line, we're saying we know that one of the variates has that particular value. So now what does the distribution of P looks like? Having known that from this bivariate Gaussian, we know this one value, what does the other look like? Okay, so that's what conditioning means. And that's what we're trying to do with the analogy. So conditioning really means there was a space of possibilities and I drew one possible value. Now I want to know what the other distribution looks like under a joint model of those two things put together. Paul has been answering that next question by Srinivas, so we'll do that. Is that the same as maximum likelihood calculation? Not 100% sure what that refers to, but we'll do that. We'll skip that for the time being. So going by what we did in the coding exercise, we look at the distribution of data and take samples from the model, but try to figure P from the data, P given data. Yes, exactly. In Bayesian statistical modeling, it's parameter, what's the value of P given data? And really, we have made a pretty big modeling choice to say there's a large space of configurations for the data. There's a large space of configurations for the model. Now let's jointly model them and see what they look like, okay? Like what the parameters look like of the model given one particular configuration of data. And I think Edward's got the right thing, just slamming all the points on the x-axis for marginalizing. That's pretty much it. Okay, so let's see. I think we've addressed most of the questions. We'll let the chat move on. So on the basis of this, I'm going to leave the hands-on like joint and conditional probability exercise. It's a second take on what's going on with joint and conditional probability. I think there's also great books by Alan Downey, Think Bayes, which you can read for free online. That really explain like in discrete terms what conditional and joint probability are. So those are great resources. So I'm going to leave this next little piece over here, like the joint and conditional probability, as an exercise for you that you can take home. What I just went through was the P of H comma D of Bayes' theorem as it relates to Bayes' theorem. And that's what we're doing in the next notebook. All right, so I'm a little embarrassed to say this, but I do have to do another bio break myself because I've been drinking so much water to keep my throat keep up with the pace. So we're gonna do a 10-minute break, and we'll come back at 42 minutes after the clock. When I'm back, I'll just start answering questions on the Q&A. All right, so we'll do that. So I'll see you all in a little bit. Okay, Maggie, so I think I've answered your question. What do we mean by config of data? And I think the easiest way for me is to actually write it out. If I have data that look like, if I did 3 coin flips, I can do HHH, HTH, TTH, HTT, etc., etc., etc. The total space is my, this refers to my total space of data. Possibilities. Now then, if I get one particular configuration, HT, then this is one possible configuration of data. Okay, so hopefully that answered your question, right, Maggie? So I see a discussion ongoing about conditional and marginal distributions. I'm not sure if this will help, but I think I do have a blog post on this. some epiphanies that I had. I'm going to put this up here just so that people can see. Yeah, this is sort of what we mean by joint, conditional, and marginal distributions. And the link is in the chat, so you all can take a look at that there. Okay, and then Charlotte's question about the bivariate plot. Is it correct to represent that a point on the plot represents the probability of corresponding outcomes to occur simultaneously? Technically, let's see here. It's the... Okay, so the height, you can imagine there's a third dimension, the height on a joint distribution. Moment. Oopsies. Oh, sorry, I blew up the wrong window. Okay, so you can imagine there's a height that's associated, or in this case, the color. If I threw a point over here, that if I am evaluating data against this guy over here, then the height represents the likelihood of the data being generated from this joint distribution. And that data actually comes to me in a event shape, right? So each event is actually two numbers, not one number, right? So yeah, so it's one event here. The event comes as a pair. So if I drew this number over here, it would be a lower x, a higher y. It has this low x, high y data has a low likelihood under this joint model, okay? And so, Charlotte, to your point, is it like the probability / likelihood? We'll let the distinction slip for to this one. I think your main question was on to occur simultaneously, and the answer is yes. All right, so hopefully that answers your question. Okay, Charlotte? Okay, so I think we're good to come back. I'm going to have y'all open up the second notebook. Okay, and the second notebook is the one on parameter estimation. Okay, the whole point about parameter estimation and how it relates to Bayes' rule. Just so we can recap, I tried to address that point over here. Right? When we're talking about spaces of models, spaces of possible data configurations. This, just so you know, was like the sticking point for me as I was learning Bayes myself. It's like, yes, I get conditional and joint probability in, you know, the cookie jar case, in all of these other cases, but like, really, how does it? What's the deep connection to Bayesian statistics between Bayes' rule and, you know, our data and our hypotheses? And just so you know, there's this like PyMC developer, Colin Carroll, and Colin Carroll has this great knack for explaining things to me. And one flight home from SciPy, he and I were on the same plane. We chatted about this on the bus ride back from the airport. And this was exactly the explanation, that there are multiple configurations of data. There are multiple possibilities of probability like models. And it's possible to, we're doing joint model. We're imposing a joint model between the two. Once you understand that deep connection, suddenly a lot of things make sense, right? We have a data generating, sorry, I'm going to come back here a little bit. We have a data generating model, right? We have a model for how, a stochastic model for how our data are coming to us. And we can use that to write things down, like the likelihood of seeing our data given a particular, given the data that we have. We can write that jointly with the parameter P that is of interest as well. So now we have suddenly two things. Okay, so if you take a look at this guy over here, so Bayesian parameter estimation. In this notebook, we're going to do this thing where we start with what we call a prior belief on our data, on our parameter P, sorry. We have a prior belief on our parameter P that doesn't reflect the fact that we're not really sure. Okay, we're really not sure about what value P should take on. So I'm going to have you open up the notebook and scroll down to that exercise down there, that code block down there, and I'd like you to fill it in fill it in over here. So first off, actually, so let's see. Usually this is done in a live setting. It would be live coded, but it's kind of difficult to do it live coded. So what I'm going to do is I'm going to have you fill it in according to what's on the instructor notebook. Ping back with an emoji, and then I'll explain to you what's going on over here. Okay?
Eric, you're on mute.
Thank you very much, Paul. Okay, great. Let me backtrack and try again. So I see the emojis coming in. This is good. I'm going to explain really quickly what's going on over here. Okay? So first off, as Hugo wrote above, what we call the posterior distribution, or the posterior belief of our parameter, or what we should believe quantitatively. That's really what we should believe about P given our data. It's proportional to, by Bayes' rule, proportional to the probability of our data given our parameter times the prior distribution on our parameter, our prior belief. So if we don't know anything, we set up a prior belief of a uniform distribution, for example. And if we believe something a little bit more opinionated, we set up something else. And we'll talk about that later. So now, if we take a look at this guy down here, the way we implement this is quite literally what's happening over here, okay? So the posterior distribution is, so sorry, let me just see here. The prior is a uniform distribution, and it's 1 because it is a distribution that looks like this guy. Let me just draw this out. The uniform ooh, that's a bad drawing. It should be a square. That's the uniform distribution. And the value of 1 inside that code block comes from the prior height. It's that over there, okay? And the way we compute the posterior is we take, we flip coins according to an assumed model, and there's a little bit of a conflation of things here. So number of successes is coin flips, right? And we compute the posterior distribution by doing this little bit of multiplication here, which this piece of multiplication, just so we decompose it a little bit, this guy over here comes from the likelihood of our data which is binomial distributed, multiplied by the prior, which is uniform of 1 everywhere. So we can do a bit of a shortcut and stick just 1 over there. And so if you start off with a uniform prior and you observe a certain amount of successes drawn from a distribution over here, then you get a posterior distribution that looks something like that. So what I'd like you to do now is to use the SciPy widgets system to interact with the posterior distribution. Try doing a few things where, one, you change the value of P, and also change the number of data points that you draw. Okay, draw from there, from that assumed probability model. Okay, and then loop back when you're done with that and put an emoji in, and tell me what you observe qualitatively going on as you vary P and as you vary N. Oh, okay. Looks like the interactive plots are not working for some. I'm using static notebooks, so it's not showing for me. For those of you who are having issues, let's see. Hang tight. I'll draw out for you what's supposed to happen. Okay. We don't need to go that many. Okay, so for those of you who are able to successfully get binder working and stuff, you should observe something that looks qualitatively quite similar to what I've drawn over here, right? So as your sample size, exactly as Srinivas has described, and Danny as well, as you increase the number of samples that you draw from that distribution, or in other words, as you take in more and more data, you see that the variance surrounding the distribution goes towards, it starts to shrink, right? And we become more and more sure. Now, if you shift the P, of course, you'll shift the distribution. And one thing that's kind of cool is that you'll end up with, regardless, the same regardless what your prior is as you reach the limit of infinite data, you get more and more and more sure of what the true parameter is, okay? So Chris has the question, 3 adds just another curve. Does n represent the number of degrees in a polynomial? No, it doesn't. It actually refers to the posterior distribution. The n represents the number of data points that are being drawn. And what you'll find is that the shape of the posterior distribution, the curve that you see at the end, is the posterior distribution. It's this guy over here. Having seen the data, this is what we believe about P, right? So what we believe about P gets updated as we see more data. And as you shift P around, that is, you shift what the true data generating process looks like, you'll see that the expectation or the mean shifts left and right depending on what the value of P is. And as you increase the number of samples drawn, you actually get smaller and smaller numbers of smaller and smaller width. All right? Are we okay with this so far? Okay, so all of this should make sense in the case of us being sort of getting more and more sure, right? Now, the choice of prior was kind of an interesting one. The choice of prior was interesting because we chose a prior that says, that looked like this guy over here. This is our prior. And it's fairly uninformative from 0 to 1. But one could argue a different choice of prior, right? One could argue that instead of, so let's set this up. Prior 1 looks like P is uniform in the interval 0, 1. Prior 2 can actually be kind of different. If we look at another prior, we might instead be interested in what we call the odds ratio. And this odds ratio piece asks us, well, what about P over 1 minus P? What would that be distributed? How would we distribute this thing such that we express that we're not sure, right? And we're not really sure about this ratio instead of this guy over here. So that's where this prior called Jeffrey's prior, which Paul alluded to earlier on, comes into play. So what we're going to do now is, so by the way, so Jeffrey's prior looks something like this. We'll give this form to you. What I'd like you to do now is attempt this exercise so you can see what it looks like in contrast, changing the prior looks like in contrast to having the uniform prior. Okay, so go ahead, attempt that exercise. Flood the chat with emojis when you're done. And I am going to answer a few questions along the way. And so we've got some responses coming in. As Lua is actually noticing exactly correctly, you can have two priors that are kind of different. So the Jeffreys prior looks kind of different from the uniform prior. What's interesting is that if you flood the prior with data, you actually will arrive at the same, you will arrive at the same, pardon me, same posterior distribution. All right. Yes, Srinivas, thank you. That's correct. Absolutely. They become very, very close. So this is sort of the prior of like reasonable people will converge on the same answer. And what's kind of interesting here is if you were instead, for example, to set the prior to be it's all of the density is at 1 and 0 everywhere else, you would never be able to change your model would never be able to change its mind on data. That's sort of the Bayesian version of an unreasonable person who, your uncle, from that opinions are extremely static and won't change regardless of what you say. All right. Okay. Maggie asked the question, did you say Jeffreys prior will give up more Gaussian distribution? No. What I was saying is that the Jeffreys prior and the uniform prior, as you add more data, you swamp the prior with data, the two distributions converge on the same value. Does that make sense, Maggie? Or they look more and more similar to one another. Okay, so let's see. Amal, can you be a bit more specific? What would you like recapped? Sorry. Suvik has the question. Does it mean that the choice of priors does not matter if we sample from a large number of data points? The answer is that's right. The choice of prior does not matter if you have a large number of data points. I do want to tighten up the terminology a little bit. So we're not sampling from a large number of data points. We're sampling a large number of data points, right? So just so that we're clear there. And then Stephen has the question, I didn't follow the introduction of the odds ratio over here. Can you say a little bit about how that relates to the uniform prior? Definitely. So let's think about what the uniform prior looks like. The uniform prior looks like this guy up here, right? So that's that's this one over here. And I think Simon's correcting me that I did say the prior converges. Thank you. It's actually the posterior converges. Thank you very much, Simon. So the uniform prior looks something like this. The Jeffreys prior conceptually is also uniform. I'm blanking right now what the bounds are on this uniform prior, but it's uniform over a different space. It's uniform over P over 1 minus P, okay? And that actually induces a different shape of a prior distribution. You transform it to P from memory. I think it ends up looking something like this. I'm not 100% sure, but something like this. I'm blanking on it at this point in my memory. It looks something like this guy over here. And this clearly has a different shape from the uniform prior, right? And so it expresses a different thing. This one says, I'm not sure about P. This is the odds ratio. And this prior says, I'm not sure about the odds ratio. That's the difference between the Jeffreys prior and the uniform P prior. Okay? Does that make sense? Okay, and then there's also this thing about like if you change the prior to a Gaussian, how does it look? How does it change? And yes, actually, if you change it to a Gaussian, it looks really different as well. And in fact, a Gaussian prior over P is technically incorrect, right? A Gaussian prior over the log of the odds ratio is okay, but you have to transform that back into non-log space and then back into P space so that you can calculate the posterior correctly. All right. So Suvik has another question. How large is actually a large number of data points? Let's see. For statistical models, I've noticed, sorry, let me backtrack a little bit. For simpler models like the binomial coin flip sort of problem that we're working with here, I've noticed that something on the order 100 points and you're good. If you start expressing, that I have to qualify that as well with, depends on like what you're trying to infer too, right? The large, I think, well, okay. Suvik, I think your question is actually related to Luke's question below. Is the point that for small n, you need a good prior? The answer is you need a prior that accurately represents your belief about the system having not seen data. Remember, the end goal of statistics isn't to show that something has a p-value of less than 0.05, okay? The end goal of statistics is to accurately quantify the uncertainty in our belief given as accurate prior knowledge that we've input into our system. Okay? So I hope that helps. And yes, Thomas, thank you so much for answering that question. Under uniform distribution, we don't know P, and under Jeffrey's prior, we don't know P over 1 minus P. Okay? All right, so we've spent 3 hours going through some of the more fundamental ideas that power Bayesian stats. The most exciting piece is what we'll spend about half an hour trying to do. But before we get into there, I want to make sure we're okay. How are you all doing with this so far? If you have any questions, let's actually, you know what? Let's spend the next 5 minutes addressing the questions that come in here. So M. Rinmoy has the question, is there a mathematical model to get the number of data required to get the optimum model? Suvik's answer is actually correct. I think we rely a little too much philosophically sometimes on some criteria of optimality. And I'm not sure we want to do that all the time. So yeah, Niels, I'm excited to do PyMC3 as well. And let's just look at one final question before we move on. When we encounter new data, I'm certain about some parameters P's value, and I'm uncertain about odds ratio. It seems an arbitrary choice, yet the choice has impact. Brian, you are correct. And I think you start with, I think the thing we won't get to, but is extremely important in maybe a real live training sort of situation, is how do you take decisions under uncertainty? Sorry, one moment. And how we quantify the difference in the decisions we need to make under different priors is actually a pretty painstaking and it's a hard process. It requires work. We're used to, automatic random forest prediction be done sort of thing. It's not that sort of thing for proper Bayesian decision making. All right. So, yes, the choice of prior has to come into play, and the choice of prior is consequential once we see how the choice of prior connects to our output of interest. Okay. So what I'm going to do is leave a little bit of a, what do you call that? Leave a little bit of an advertisement, I guess you can say, for an updated version of what we're going to be of the tutorial. Hugo and I have also, coincidentally, just like Raveen and Junpeng and the others doing a follow-up book, we've actually inked a proposal. We're working with Pearson on a proposal to do also a Bayesian book, but with a little bit more of the focus on the fundamentals and taking it all the way to decision making. Connecting fundamentals all the way to decision making with Python, PyMC4, which we're targeting. And there'll be a cookbook of like recipes for analysis that you can use as well. So I'd keep your eye peeled for at least the updated version of the tutorial repository. Okay. All right. Cool. Great. Let's go on to PyMC3 and parameter estimation. Okay. Because I think this is where it gets really interesting. So what I'd like you to do is go down. We're going to use the click-through rate example because it's easy enough to understand. It's an easy enough way. It's an easy enough model to understand, and I think it'll help us over here. So with PyMC3, we need data and we need a language for specifying probabilistic models. And that's what PyMC3 provides. So if you continue on down below in notebook number 2, you'll get click-through rate. There's one code cell over here, which will give you like click-through rate data, simulated data. All right. Now, how do we build a model that expresses the uniform unknown P plus the likelihood? Well, the way that we do it is with this sort of syntax. And now let me guide you on, I think, the most practical way to approach building your models in PyMC3. So first off, you actually start with the likelihood of the data. So we work backwards from the likelihood of the data. We say that our data, Y, for example, are drawn from a binomial distribution where N is known, P is unknown, so we'll give it like a placeholder random variable that we'll define later. And we say that because this is the data likelihood, we're going to condition on seen data by passing the seen data into the observed keyword argument, right? And seen data usually should be like a numpy array of some kind. Then we work backwards. We know that prob was the thing that we didn't know. We don't know P precisely. So we define a second probability distribution for prob, and it's the uniform distribution. The default keyword arguments are lower bound 0, upper bound 1. This string that you see over here, it refers to the name of the random variable. By convention, Hugo didn't stick to that in this notebook, but by convention, we simply take the same name as the Python variable that we're using. So over here, P, by convention, we would actually name this P. And all of this goes inside a model building context, right? So with pm.model as some model. And this model, this guy over here, you can name it anything you want. You can call it coin_flip_model, and that's totally cool as well. And with that, you get an extremely intuitive syntax. And by the way, the most pragmatic way I've seen of building these models is to go backwards from the data back into the necessary prior distributions, okay? And then once you have that, you get what we call the inference button. So prior to this, pun unintended, we actually hand calculated the posterior. I see a few people are having some troubles. If you go into notebooks/SciPy 2020/instructor, that's where it is, all right? It's under the Bayesian estimation piece. So if you go, what happens here is then you can hit the inference button, and what will happen over here is that there's this sampling from the posterior distribution that is happening. We're not explicitly calculating the posterior distribution like we did above with the Jeffreys and uniform and Gaussian priors. Instead, what we're doing is we're calculating it by sampling. Now, again, what happens underneath the hood with PyMC3, we're actually, the goal here is we try to abstract it away from the end user. However, if you're curious as to what's happening underneath the hood, I actually wrote an article for myself that explained it. And so I can now point people to it whenever there's a question on that. What exactly is happening underneath the inference button in PyMC3? So let that load under this tab. Give it a moment. Over here, that's the one. And I'm going to paste this inside. That's what's happening underneath the hood every time you hit pm.sample. That is what we're doing when we're trying to calculate the posterior by sampling. Then it'll look like what you see over here. Okay? You'll get a posterior distribution that is simulated or sampled from this joint model between the data and our likelihood, okay? And that will give us the posterior distribution. Okay, so I think I'm starting to get a few questions over here. Bharat, I need a bit of clarification which piece you would like recapped. So can you put that inside the questions piece? And so meanwhile, you can build a second model. So this is one way of expressing that coin flip model, basically. And if you were to put a different prior, if you were to put in a different prior, so you could express it, say, with instead of a uniform P, you might choose a different probability distribution. Say, for example, a beta 2-5 distribution, and that might be another way to express a different kind of prior. Okay, so. All right, so got a few questions going up. Bharat's question, build a model of P. Sorry, Bharat, I need a bit more clarification. My mind is going to mush right now on what you would like recapped, because that is the syntax for building a model. We go backwards from the likelihood, condition on data, and then we add in, well, this is the piece that we're not sure, so we add in some priors on there. So not sure what it was there. Steven's got the question, why is this written for context workflow when a model isn't used in either context? Okay, so the design choice is more software than it is, it's more for software reasons than it is for statistical reasons. When you build a model, you need to build a computation graph of some sort that looks something like this, basically. I'm going to draw it out. Oops, sorry. You're building a computation graph that looks something like this, or a probabilistic graph that looks something like that guy. Okay, so, and in order for all of this information to be correctly inserted into the model, I think that the programming choice was, or rather, in order for this dependency that you see over here to be inserted into the model, we need to, we use a model context so that we don't have to keep doing like model.add something, model.add something, model.add something. The context manager helps with the way the context manager has been programmed, allows for this kind of construction to go, allows for this kind of question, model construction to happen, right, underneath the hood. And then Charles has the question, should we be concerned about the warning that the acceptance probability does not match the target? Not at this point, because right now we're still trying to emphasize, what's the syntax for building models, emphasizing how it's a little bit more, emphasizing just how the syntax matches how we would write a probabilistic model. And so, that's for this reason, for now, ignore it. However, if you go to Ravine and Collins' tutorial from last year's SciPy, they address these issues in their tutorial. All right. And then Ken has the question. So the prior model need not represent the data or the model. Put another way, the prior model need not represent the model, correctly model the data. It's just a starting point. The answer is correct. It's essentially what you believe about that parameter value, given what you believe about the parameter value, given having not seen the data. Sorry, there's no given inside there. So if you believe that the coin flip really should be fair, you can actually draw out a distribution that looks something like this. And this might be a beta distribution 5,5 sort of distribution. I'm sort of not going to harp too much on what the beta distribution is, but that's just another way of expressing a different starting point for the model. All right. Okay. Cool. Do we have any other questions here so far? So I think one thing you might want to do here is think about this next question. I think this is kind of interesting. This is click-through rate data. You have a non-technical manager. What would you tell your non-technical manager of your growth team about the click-through rate? Pardon me, I have to take a quick break. All right, pardon me. Sorry, everybody. I had to do a quick bio break myself. Let's see here. So first off, Amanda has the question, what does HPD in the graph mean after line 10? Yes. Okay, so there's this concept of the posterior density and sort of so keep in mind, total area in the posterior density supposedly sums up to 1 if you interpret it as a probability distribution. the 94% HPD refers to where 94% of the density is located, right? So it's, in this particular case, it's located in between the bounds of approximately 0.14 to 0.24 or something like that, right? So and it's a metric, by the way, that is debatable as to whether it's a meaningful thing, but right now, for now, it has been popular in the past. I think people are in the Bayesian stats world, we're reviewing whether it's really applicable or not. Or sorry, how suitable it is as a way of quantifying our uncertainty. I think the nicer way really is we calculate the quantiles and we say that the posterior distribution, the 10th percentile and the 90th percentile fall within this particular range, and that's good enough for expressing what the uncertainty is. So hopefully that answers your question, Amanda. Okay. So do we have answers on what you would do about your, this click-through rate interpretation piece? Srinivas says mean is approximately 0.1 and distribution mean shows around 0.14. Why are they different? You might have found a bug. I'm not 100% sure. Or there could have been like, no. I think what we're seeing here is we're simply seeing the rounding off on the bounds over here. Yeah, it's a rounding issue. So one thing that we might say is, first off, we are reasoning about the posterior distribution of P, having seen the data, and the way that we're doing so what we're calculating here is the posterior distribution, and we're really reasoning about what we expect to see about the value of P. Some of you are mentioning that the plot isn't centered at the starting point, and we know we started at 15% click-through rate up here, but the mean is nowhere close to 15%, right? And that's because if you look at the data that were generated, then that might give you a different answer. Okay, so for those of you who are able to do so, I'd actually like you to try the next exercise. This is what we would call the simplest complex example that also relates back to some of the things that we might have learned in classical statistics. Okay, so I'd like you to try this next hands-on exercise over here. And so I'll have you finish up all the way till over here. So when you get to these two, we'll consider that the exercise is done. So give me a thumbs up when you're down over here, and I'll walk through the example, particularly the model building piece. Just so that others have the code up in case you're sort of stuck. So Scott's got the question, which notebook am I in? Notebook 2, instructor version under the SciPy 2020 notebooks. This is an issue that we must fix. We really shouldn't be doing, each conference gets its own notebook. It's a little confusing. So Robert's got a question. Suppose I have 1,000 data points, no great confidence in my prior. Is it legit and software supportable to start with an uninformative prior, apply to the first 100 data points, and then use the posterior estimate from that as my prior for the next 900 data points? The answer to legitimate is yes. The answer to software supportable is it's a little bit trickier. Here's why it's principle to do this with why it's legit. As you, all we're doing is Bayesian updating, and so if you take your posterior as your new prior, then you've basically got updated beliefs. That's the philosophical way to think about it. You have an updated belief, and so now your new belief can be transferred onto new data. And what I mean transfer to new data means you're allowed to say, that's what I believe now. It's my new prior for evaluating and calculating under uncertainty for new data points. The software tooling is a little tricky. So if you look on the PyMC3 website, there are examples of how to do that, right? So I hope that answered your question, Robert. And Maggie has a question. So in this notebook, it's the same thing as notebook 3 plot posterior, but we're utilizing a library to do so. The answer is correct. Yes, exactly. So previously, at the top of this notebook, we actually calculated posterior distributions by hand. And in this case, we're using PyMC3 to estimate the posterior distribution using Monte Carlo sampling. Okay, so hopefully that answered your question, Maggie. And then Lou had the next question, which is how can PyMC3 identify which variable is for prior and which is for likelihood in box 13? The answer is exactly by the observed keyword, right? So when we observed is equal to this, we're saying that this particular random variable, we've observed the data for that random variable, this random variable over here. And so therefore, we're actually conditioning the entire model on a configuration of data, right? And finally, Andrew has the question, what's the state of progress for PyMC4? We need a progress bar. And TensorFlow probability has not been forthcoming on the progress bar because we've delegated all of the sampling to TensorFlow probability because it's supposed to be scalable and everything, but they've not been responsive with respect to a progress bar. Okay, and so we've got a few other comments. Amal is asking, we have a belief and it's expressed by P. Now a bunch of data comes in. I want to revise my belief about the P, not the data. We want to revise our belief about the P, which is done by P given D, which is correct. That is correct, Amal. Okay. And then Eshin has the next question, or actually it's a comment. Yeah. The line should be n successive. Okay, thanks for the comment, Eshin. And then Thomas says, do we need a progress bar and getting a progress bar? Yes. Right now it seems stuck at 0. All right. All of us on the PyMC dev team are not really happy about the lack of movement from TFP on the progress bar, because the progress bar is kind of like one of the best hacks ever. Okay, so what I'm going to do for the rest of the for another 10 minutes. Bad initial energy, Falk, is something that we'll have to address in how do you debug a model. But bad initial energy usually means there's a data or a distribution that can take on values that are invalid for the set of values that are expected. So I give you an example. If you placed a Gaussian prior on, sorry, bad initial energy for the progress bar. Yeah, that's right. Okay, so let's go to the Bayesian hypothesis testing piece. I think it's worth at least me talking through for the next 5 minutes or so we can at least get an idea of what's happening. So what you've seen above up here, Vincent, I'll get to your question in a moment. What you've seen above up here is estimation for like a group, a data that belongs to a group. So for example, finch beaks that came from the Fortis species, right? This guy over here. There's another species called scandens. there's another species called scandens. And so right now what we've done is we've only done fortis beak length estimation. We've not done anything else, okay? And so this is our belief about fortis beak length means and their variances, having seen the data. We believe that the mean should be around this location and the variance should take on about that sort of scale. When we think about Bayesian hypothesis testing, I'm going to skip past click-through rates. I think it makes sense to stick with the same example. When it comes to Bayesian hypothesis testing, what we're interested in here is comparison between two groups, right? We're looking not at a single group, but two groups together. And so what we can do is we can compare, for example, the difference between the means as well as the effect size as calculated by the estimated parameters that we have. For me, so when we construct the model, we construct our model with priors for each of the particular groups, okay? This is the prior for the fortis beak length, and this is the prior set for the scandens beak length. Now, if we want to calculate the difference in the means, which is sort of what we would be doing if we're doing t-tests, for example, we would calculate it simply by taking these two random variables and taking their difference. And to calculate the effect size, we do yet again deterministic transforms on our random variables. Here's why this is really cool. We treat each of these random variables as nothing more than math objects that we can manipulate and calculate in the same way. And for free, after sampling, we get the difference. Not only do we get the difference, we get the uncertainty in the difference. Not only do we get an estimate of the effect size, we also get the uncertainty in the effect size, okay? So this makes it kind of really cool because you get all of these uncertainty estimates of key parameters for free. What is really cool here is, let us say you had a different problem, not beak lengths of finches. It's instead a problem that involves money. And you know that some dollars are going to be spent on the basis of an estimate of certain parameters. Now you can write a cost function, a money function that is a deterministic transform on your parameters and get the full uncertainty in, say, for example, how much you expect to spend or how much do you expect to earn, given that history stays the same and future populations, the future behaves in a static way that is similar to what we've estimated from historical data. I'm going to pause here for a little moment. Are there questions on this point? Because I think it's a really cool reason why we would want to use, more generally speaking, an expressive probabilistic programming language. PyMC3 is one of them. You can do the same with Stan. You can do the same with Pyro. TFP is a little bit more low level, so you can do it like a little bit more. TFP is a little more low level, so you need a little bit more Python work. But the core idea is there. You can actually calculate things that are deterministic transforms on your random variables and calculate stuff that is of interest. So now I'd like to make sure we're okay with this. And if you have questions, stick it inside the Q&A box, please. Okay, so Niels has the question, what's the intuition behind the effect size calculations, diff means divided by pooled SD? So let's see. What we want to see is that the effect that we're observing is greater than the effect that we're observing is greater than what we would expect to see by random noise, right? So the pooled SD gives us a measure of the inherent noise in a system, or inherent noise in how we're observing stuff. And the intuition here is that the difference should be greater than the scale of the noise. For example, a great intuition would be if you're in astrophysics world, right? Kilometers of difference between stuff is fine because kilometers of difference between stuff is actually like inconsequential. However, if you're an ecologist, kilometers of variation, what am I saying? Kilometers of variation in astrophysics is small. Kilometers of variation in ecology is big. So if your differences are bigger, like in astrophysics, your differences are on the light year scale. Kilometer is nothing. So your effect sizes are going to be large. If the noise in your system, distance measurement, for example, is on the kilometer scale. But in biology and ecology, if your like ecological system is, is a microbiome, and you're talking about like millimeters of difference between stuff, then that variance in distance is a lot relative to the difference. So we can't really say much about the effect size. And Steve is saying it correctly. It's also called Cohen's d. That's another way. So hopefully that helps. Hassan has the question, why deterministic and not stochastic? Okay, so why deterministic and not stochastic? It would be it's a deterministic transformation. We use the deterministic keyword because it's an exact, this thing minus that thing, or this thing plus that thing. There's no randomness in the math function. That's why this deterministic thing shows up. Okay, so then the next one by Eschen is, can you discuss conventions for how to pick parameters for the prior distributions? Specifically, with culture, they calculate the mean SD, use those as the parameters for the normal prior. If you do that, you are running into the realm of empirical Bayesian sort of analysis, modeling protocol. People debate whether that's okay or not. And I think it's always better I think the truly principled fashion of approaching this modeling task is to not look at your data, if you can, before you calculate the mean and standard deviation. However, you do need to check your priors against other people and ask. This is why Bayesian model building is not one of those automated protocols that you can go through. It involves a lot of debate, sometimes consensus building that needs to happen amongst your team. Like, this makes sense, this makes sense. We all agree on it. We can defend these choices in front of other reasonable people. And so, yeah, it's a very scientific, I'd say, way of doing that. Back to the question, if you do go empirical based, then you have to have a good rationale for doing that. You can say something like, I really don't have any other ideas. Do you have other ideas? I think as a matter of workflow, when we're debating with other people, if you disagree with a prior, you should come up with another prior and justify that prior. It's not enough to say, I disagree with your prior and not provide an alternative. Okay, so hopefully, Eschen, that answered your question. Anna had another question. So the key is that your modeling distribution not means like in linear regression. How could you apply MC to making predictions in time? The answer there is to look at Thomas Wicky's blog post which Falk has kindly pasted inside there. And so the more general point is, if you look at how you do time varying predictions, right? You still have to have a model of how your key parameters of interest are going to vary over time. So in the example blog post that Falk posted inside the chat, the key parameter of the Gaussian mu is assumed to vary by a Gaussian random walk. And that's a modeling choice, and a random walk inherently means the next mean depends on the current mean, but it's got another Gaussian distribution on top of it to determine where the next mean happens. So you do have to think a little bit about the data generating process. And I think it's a very valuable exercise to actually sit down and do something like what we did with our generation of coin flips, and try to simulate forward simulate, if you want, like an adjective, forward simulate how our system behaves by explicitly programming it, right? And using probability distributions at the places where we don't exactly know what the outcome is supposed to be. So, key example, if my P in a binomial, or if my P in a coin flip is thought to change over time, then what I might do is write down that P is drawn from, P starts at some value, and then as time progresses, it takes on a new value, and I get to write the rules for that. And then at each time point, I draw a value, and over time, I'll get a sequence of ones and zeros. Okay, and so you can take a look at that. You can look at that process, like explicitly simulate and model that process. Okay, so Anna, I hope that answered your question over there. Next one, is there a logical relation between hypothesis and the chosen priors? In our case, is our hypothesis, null hypothesis, that the beaks of the two species are of the same length? Falk is correct in saying the priors should not reflect the hypothesis. You look at that in the posterior distribution. Now, because of time, one thing I didn't really go through was how do we well, actually, no, we did go through it. We looked at the difference of means. Sorry, I had a brain blankage, blank out just now at that point. When you look at the difference of the means, that is effectively what we're asking. Does this posterior density cover zero? If you actually read a paper by John Krushke, it is Bayesian estimation supersedes the t-test. I'm going to give y'all a link to that PDF. There we go. If you read John Krushke's paper on the BEST paper, it's BEST for a reason. Bayesian estimation supersedes the t-test. So there's really no null hypothesis. You can actually get much richer information out of the posterior analysis than you can with a simple t-test. And I think this relates to Srinivas's question. Is it similar to the t-test where you compare means and ANOVA where you compare variance? Yes, though like I mentioned, you do get much richer information. So for example, I'm going to go back up to this just so that we can show you like the sigmas. If I have a sigma for Fortis and I have a sigma for Scandens, okay, those two, and they can be wildly different. Sigma for Fortis could be 0.7 to 0.9. Sigma for Scandens could be some other number, say 2 to 3. You might actually come to a biological hypothesis or an ecological hypothesis on the basis of the variance, not the means. when you see low variance, usually that's an indication of high selection pressure. And when you see high variance in the phenotype, that's an indication of low selection pressure. So you can actually, on the basis, like I was saying, if you were to do this in a t-test fashion, like I was saying, you end up with this very narrow definition of what you're trying to analyze. But with a posterior of mu's, comparing posterior mu's and comparing the posterior on the sigmas, you actually get a lot more richer information. Okay, so hopefully this addresses both of your questions. We'll do a few more, and then I will wrap up and by pointing you to some other resources at the end of this. So just do two more. So the first one is, can we reframe the hypothesis testing problem as a regression model? Vincent, I'm going to have you, let's see. I'm glad you asked that question, because as we're writing up a rewrite of the tutorial material, I'm seeing that there's all these questions that you guys have, including this one. They can be addressed with a little bit of a reworking of the order of how things are presented. And regression is a natural extension of estimation. It's when regression modeling happens when we think that something predicts another thing. So right now we have not brought in any predictors of the means or the variances, but we can, right? We can. So I'm going to have you sit tight and wait for the updated version. I'm working on this in my spare time with Hugo. I'm very excited to refresh the repository. I've unfortunately was a little bit swamped with work, so I couldn't get to updating it for this particular instance of the tutorial, but it should address your question. The short answer is, hypothesis testing as a regression model happens only when you have predictors that are of interest. All right. So hopefully that answers, and we'll do the final one. We'll do a final one that someone hasn't really addressed. Okay. They've all been addressed. Paul has got an answer to Roy's question. Let's see. Yeah. Paul's got a good answer to that. So I'd encourage you all to check that. I think Seth's question, this might have been answered already. How can I predict plots? Which plots from our model will be shown by default in AZ.posterior? You use the var names, and that's it. So actually, I think I'll just we'll address Kelvin's one. In a real world setting, when do you decide to dive into coming up with a parametric Bayesian model as opposed to something like a GP? The key idea here is when I can come up with what I think is a reasonable data generating model, then I won't worry about a Gaussian process. A Gaussian process comes when we really don't know how inputs and outputs relate to one another, and we still want a way to be able to get uncertainty estimates out of such a model. Okay, Kelvin, I hope that answers your question as well. Okay, everybody. Thank you for sticking around. We're gonna end the tutorial here. I really want to encourage you all to keep your eyes peeled for for more updates to the tutorial repository. It's always a work in progress. Even the other tutorials that I teach, network analysis and deep learning, they're always being updated all the time. So keep your eyes peeled for additional updates. I'm really excited for the reworking that introduces explicit simulation with probability distributions into the whole tutorial. And it will be a lot more in-depth into how we addressing all of these questions that you have here, which is, how do you make these decisions? How do you decide between things? So keep your eyes peeled. In the meantime, there are other great tutorials outside that are available online. I highly recommend, if you feel like you need a refresher on the fundamentals, go look for Alan Downey's tutorial last year and pick up his book, Think Bayes. If you want to go a little bit deeper into the decision-making process, go into Ravine and Collins' tutorial from last year as well. They go into a lot of the diagnostics and all of that stuff. Keep your eyes peeled for updates to our repository. We're writing a book as well, so keep your eyes peeled for that too. And keep an eye out on PyMC4. PyMC4 is, apart from all the little warts that I mentioned and sort of pseudo complained about, it is actually getting a lot of attention and love from the PyMC devs. It's just TFP and Google that's been stalling for us. So help us by coming onto the issue tracker, voicing your concerns. If you've started playing with PyMC4, voice your concerns, especially about a progress bar. We need the progress bar. And so we'd love to see you around and actually hear more. Write blog posts, by the way, about stuff that you build, models that you build. I will be posting a few other resources, like, for example, the Bayesian analysis recipes repository, which will give you a starter collection of models that you can use going forward. All right. Thanks again for everybody for coming. I hope you enjoy the rest of SciPy, the virtual SciPy 2020. There should be a feedback form that gets sent out. Please do fill it in. We'd love to hear how we did, and especially how we can improve, things that really, things you want to know more about. All right. So thank you very much, and hope you have a great day.
All right. Thank you, everyone. And thank you, Eric. That was really awesome. I think we all enjoyed that tutorial a lot. Following this, feel free to move into the next session at 1:45 for the welcome remarks. We hope to see you there. Thank you.
Thanks a lot. And thank you, Emily and Paul. Also, send out a shout out to Hugo if you get a chance. He made the bulk of the material that was presented today. He's on Twitter, and I'll send his ID handle by Slack. All right. See y'all.
Awesome. Thank you.